Okay, a quick recap and a new result with respect to phase transitions. We know that the amount of thermal energy that's required to make a substance change phase is m times L, where L is the latent heat. Now, as a for instance, consider water. Now, water actually evaporates at all temperatures. And above the water's surface, there's a mixture of water vapor and air molecules. So that's H2O in the gaseous state. That's what water vapor is. Now, there's an equilibrium process whereby, say, water molecules or the more energetic ones are absorbing a bit of energy from their neighbors, and then they're changing into the gaseous state. The reverse process also happens where gas molecules, say, maybe collide together, and in so doing, actually condense and go back into the liquid state. Now, if we look at the water surface, so here's the liquid surface here, then above the water, there's going to be oxygen, there's going to be nitrogen. Remember, 78% nitrogen, that's air, right? And only 21% oxygen. So there's air here, but there's also H2O molecules close to the water surface here. Now, something known, the vapor pressure, we should define that. The vapor pressure, that's just the pressure that comes from these H2O molecules. It's otherwise known as partial pressure. So it's the sum of all the collision forces coming from just the H2O molecules. So to be clear on this diagram, this is the water, and then this is the air space above the water, which contains oxygen, nitrogen, but also molecules of gaseous water. Now, as temperature goes up, the partial pressure actually increases, meaning there's more water above the surface than there was before in the gaseous state. Now, eventually, the partial pressure will increase to atmospheric pressure, meaning that all the 101,325 pascals newtons per square meter of collision force is coming only from the water molecules. So this is the boiling point then. So when it's boiling, the vapor pressure is now 1 atmosphere. So that defines the boiling point. Now, at 100 C, not only do we get evaporation from the surface, we also get the phase change happening within the bulk of the material. So you get bubbles forming. Now, during that phase change, the temperature will remain constant, so boiling water stays at 100, while all of the water changes into the gaseous state. There's actually a couple of ways that we can find the thermal energy. First of all, as we've done previously, a little bit of dq causes an amount dm to change phase. L is a constant, so it comes out. And then integral dm is just the mass. So mass times latent heat. That's the Q. We wrote that down earlier. The other way, though, is we know that in terms of entropy, the ds is dq over t. So dq is tds. Now, because the temperature remains constant as we're undergoing the phase change, that's just T integral ds, and we're starting, let's say we're going from a liquid to a vapor. And let's say, so in that case, this would be the latent heat of vaporization. And so this is going to be T times the entropy of the gaseous state minus the entropy of the liquid state, because the integral of ds is just S. Okay, and those terms are defined here for us. Now, another way to proceed is to, first of all, start with the first law, then rearrange and solve for dq. So it'll be du plus pdv. Now, because at a constant pressure process, VDP is 0, so therefore, this term if we were to expand the d of PV, we get two terms. We get PdV plus VdP. But we've just said that this one is 0 in this case. So the point we're heading for is that I can write this as the d, the differential of pressure times volume. And consequently, I can say that dq is the d of u plus PV. Because expanding this and then inserting the fact that this is 0 will get you back to this line. The reason that's useful, of course, is that is dH, the differential of enthalpy. Just let me pause there for a second. Since dq equals dH, then we're just integrating dH from the liquid state to the vaporous state. So that just is the enthalpy of the vapor minus the enthalpy of the liquid. So we see that there's several equivalent ways to find the thermal energy associated with the phase change. I'm looking at vaporization. This would be true for fusion as well. But because we're going to focus on vapor pressure for a bit, I'm dealing with the liquid to gas phase change in these equations. So it's m times L, it's T times the entropy change, or it's the change in enthalpy. So, as we said, we want to look a little bit more at vaporization, and we want to calculate a result related to the vapor pressure, which is known as the Clausius-Clapeyron Equation. So, with vapor pressure, as we've said, we've got some gaseous water that's above the liquid surface, and there's an equilibrium process. So if you were to suddenly, say, heat up some water, what would happen is more of the molecules would start to evaporate. You'd have a net flux from the liquid state into the gaseous state, but they're going to start to collide, and so then the rate of condensation will increase as well, and eventually the two rates will be equal, and you'll have an equilibrium process, and the rate of evaporation will equal the rate of condensation. Now, typical vapor pressures, well, they're not very large, right? For water at 20, it's 2,300 pascals out of 101,325. Ethanol, a little bit higher, propane, extremely high. And these represent the volatility, how readily the liquid evaporates, right? So that ethanol, being an alcohol, evaporates a lot more readily than water does. And propane, of course, has a huge vapor pressure there at 20 degrees C, so evaporates very readily. So we're going to now derive this equation. Evaporation is a change of phase that happens at constant temperature. So we're going to look at our Gibbs function here, U plus PV minus TS. Then we're going to do its differential. This will be du. There'll be two terms here from the product rule. It'll be the d of PV, so that'll be PdV plus VdP. Again, we'll have to product rule here, so it'll be minus TdS minus SdT. But recall from our first TdS equation that we can replace du with TdS minus PdV. As a result, this term and this term cancel, and the minus PdV and the plus PdV terms cancel. So when we put this in here for du, we're left with only two terms for dg. It will be VdP minus SdT. Now, phase changes, we said, have constant pressure and temperature. So dP and dt will both be 0. dg is 0. The Gibbs function is a constant. So along the isotherm and isobar, the value of the Gibbs function is not changing as the water absorbs its latent heat and changes from the liquid state to the gaseous state. So here is the phase surface for water, and we're now going to look at it from the pressure-temperature side. So we see here the line separating solid and liquid. That's this line right here viewed from the side. Then we have this line here that separates gas and liquid. Well, that's just looking at this dome from the side and seeing this right here. Now, we're interested in the shape of that curve, which is the shape of this one. And when we view it from the pressure temperature side, we see it looks like this. So we know that during the phase change, the temperature and pressure will remain constant as we move from the gaseous to the liquid state. On the PT side, that's just moving from here to here. Okay. Now, if we are going to, say, increase the pressure a little bit, as the pressure goes up, the temperature goes up too. So we're just moving a little bit along this curve. And we want to know how that changes things. Okay? And this will lead us to the Clausius-Clapeyron equation. So how does the pressure and the temperature, how are they related along this coexistence curve? Well, let's go back to the Gibbs function. dg is vdp minus sdt. Now, when we move along that coexistence curve, there is going to be, as we say, we've increased the pressure a bit, we've increased the temperature a little bit. We will eventually come back to an equilibrium point where the Gibbs function, the value of the Gibbs function for the liquid and the vapor is the same. So at that point, the change in the Gibbs function for the liquid and the change in the Gibbs function for the vapor will be the same, because these were the same values before. We've changed a little bit. We're back in equilibrium. They're now going to be, the total Gibbs function is the same, but because these were equal before, the changes must also be equal. So, well, what are the changes? Well, we can use this differential here, and so we can say minus S of the liquid plus the volume of the liquid dP, and now substituting in the vapor values, is going to be minus S of the vapor dt plus the volume of the vapor dP. So we can next gather like terms. So putting the dP terms on one side and the dt terms on the other, we arrive at this. And then solving for dP dt, which is going to be the relationship between pressure and temperature, we find it's the entropy change over the volume change. Now, that entropy change, we saw it in our derivation of latent heat, and so we know that this is related to ml over T. We're also going to make the approximation that the volume of the vapor is much bigger than the volume of the liquid, so we're going to drop the liquid volume term. So making those substitutions, we get dP dt is ml, and that's going to be understood to be the latent heat of vaporization, over T. Right, so that's for the entropy change, ml over T. Then we still have to divide by the volume of the vapor, having made this approximation here. Now, if the vapor is an ideal gas, then PV is over nRT, or 1 over V is P over nRT. So we substitute that in. So then we get MLP over nRT squared. Now we're going to introduce the molar mass, which is just the ratio of the mass to the number of moles, right? It's the kilograms per mole. So that's mu. And then we're going to solve for the pressure. So the way we solve for the pressure is by separating the variables. So we get dP over P. So m over n is mu. Then we have L over R. And then we've got dt over T squared. So now we're going to integrate that. And we're going to integrate from a reference pressure and a reference temperature up to a final pressure and a final temperature. And again, this is integrating along this liquid-vapor coexistence curve and trying to find out what the shape is when we're starting at a knowing point and we're going to another point. So we're increasing the pressure a bit and we're saying, okay, what's the new equilibrium vapor pressure at that point? Okay, so this side's pretty easy to do. That's just a logarithmic integral. So that's the ln of p over p naught. This side's also easy to integrate. Integral of t to the minus 2 is minus 1 to the t minus 1. Minus 1 over t. So this is negative mu L over r. Then we'll get 1 over t minus 1 over t naught. Now, we will solve that for pressure. Oops. Give myself a little bit more room there. And we get pressure, we're going to add some subscripts in a second, is p naught, and then it's e to all of this. So it's e to the minus mu L over r 1 over t minus 1 over t naught. Now, t naught and p naught are the reference points. They are a known value of the saturation, vapor pressure, and temperature. So really, I should have a few more subscripts here. I should say it's p naught, it's the known pressure of saturation vapor pressure, and this is the unknown value a little bit further along the curve that we're trying to find. Okay, and this is the Clausius-Clapeyron equation. So, the shape of this curve, then, we've shown is an exponential function. Oh, where did it go? Here we have it here. It's pressure naught times e to the minus constant 1 over temperature. So this is an exponential function. And what we're doing is we're starting off at some known point, and a good point that we'll use is the triple point right here. So that's 273 Kelvin. The saturation vapor pressure is about 610 pascals. And so that will be our P naught, our saturation, known saturation vapor pressure at this given temperature. So if we wanted to go to a higher temperature, say at 373 Kelvin, the boiling point, what would be the saturation vapor pressure at that point? So we can use the Clausius-Clapeyron equation. And we're going to substitute in here. Okay, so now mu is the molar mass in SI units. So mu, that's 18 grams per mole, or 18 times 10 to the minus 3 kilograms per mole. That's a 3. And so we're going to do this in the EXP format. So this is 18 times 10 to the minus 3 kilograms per mole. L is the latent heat vaporization. That's 2,256,000 joules to vaporize a kilogram. And we divide by the ideal gas constant, 8.314 joules per mole Kelvin. The temperature that we're trying to find is 373. Our reference point is 273 and a vapor pressure of 610 pascals. So the saturation vapor pressure at 373, according to this equation, is 73,867 pascals. But of course, we know what it should be at 373 because that's the boiling point of water. It should be 101,325. So we've actually got something a little bit less than expected. Now, there's several reasons for that. We made a couple of approximations along the way. It's also true that the latent heat isn't constant, and it varies somewhat with temperature. But we're in the right ballpark. We're within 25%. It's not that bad. And we've actually integrated over quite a large range of temperatures here. Over a much smaller range, the Clausius-Clapeyron equation is a lot more accurate. So, there we go. We've got, excuse me, the equation relating saturation pressure to temperature along the liquid and vapor coexistence curve. And there's lots of interesting things that we can do with this, and we'll look at that in class.